In part 1, we began the proof that shows the equivalence of these two definitions of a closed set by first proving that if A contains all of its limit points, then that implies that the complement of A is open. In this video, we complete the proof of the equivalence of these two definitions of a closed set by proving the other direction of this equivalence statement. That is, by first supposing that the complement of A is open, and then proving that that implies that A contains all of its limit points. So how do we prove that A contains all of its limit points? Well, we're going to have to prove the following implication. If U is a limit point of A, then that implies that U is in A. This is what we're going to prove. Now, to prove this, we first let U be any possible limit point of A. So let U be any limit point of A. Now notice, our set A lives in the metric space E. So U also lives in the metric space E. It wouldn't make sense to talk about U living in any other metric space. So we can say that U is in the metric space E. But check this out. I've proven in my set theory videos that if A is some subset of some metric space E, then that metric space E is equal to A unioned with the complement of A. So this means we can say that U is in the union of A and its complement. And by definition of set union, this allows us to say that U is in A or U is in the complement of A. I've also shown in my set theory videos that a set intersected with that set's complement is equal to the empty set. So in our case, A intersect with the complement of A is equal to the empty set. Or sometimes people say that A and the complement of A are disjoint. But this statement of course makes sense because the complement of A is all the points that are not in A. And because A and its complement are disjoint, we can now be more precise and say that U is in A or U is in the complement of A, but not both. But not both. But look at what this allows us to do. This allows us to focus our proof on ruling out the possibility that U is in the complement of A. And if we're able to show that U can't possibly be in the complement of A, then the only other possibility is that U must be in A. So our new goal is to prove that U is not in the complement of A. Now, as is usually the case, something that's going to help us prove this statement is leveraging what we know. And the two most important things that we know right now are the facts that the complement of A is open and that U is a limit point of A. Well, we can already use the fact that U is a limit point of A because we're dealing with U here. But in order to use the fact that the complement of A is open, we're going to have to prove this statement by contradiction. That is, we're going to have to suppose that U is in the complement of A, and then derive a chain of implications that leads us to a contradiction, thus implying that U can't possibly be in the complement of A. Well, what happens when U is in the complement of A? Well, check this out. We're now able to use the fact that the complement of A is open. And if U is in the complement of A, then by definition of an open set, there exists an open ball centered at U entirely contained in the complement of A. So every point in this open ball centered at U is in the complement of A. But that's the same as saying that every single point in this open ball centered at U is not in A. But wait a second, we're saying that this implies that there exists an open ball centered at U such that for every point P in that open ball centered at U, P is not in A. But wait a second, U is a limit point of A. And by definition of a limit point, For every single open ball centered at U, there must exist some point in that open ball besides U itself that lives in A. So if we were to suppose that U is in the complement of A, then we would arrive at the contradiction that there exists an open ball centered at U entirely contained in A, meaning that every point in that open ball centered at U is not in A, which is contradicting the fact that U is a limit point of A. So therefore, you can't possibly be in the complement of A, because otherwise, if we were to suppose that U is in the complement of A, we would arrive at this contradiction. So therefore, U must be in A. And since U is any limit point of A, every limit point, any limit point of A, must be in A. And we're done.